Okay, so I did these calculations in MathCAD, and I'm happy to put them up on the smart side for you. So let's look at how I did this. Okay, so here's my trial function. This is one we talked about already, u of x. That's exactly what I wrote on the previous slide. And then, as I said, the axial strain at a given point x along the beam is equal to 1/2 du dx squared. And so now I've evaluated that. And so this is the axial strain at a point x here. And once I calculate the derivative here in MathCAD, this is what I end up with. So the total axial strain is the integral along the length of the beam here, and I called that epsilon sub a. Okay, so the axial strain here. And I evaluated this integral, and so what we end up with is this is the total axial strain. Okay? And so this axial strain is the axial strain basically anywhere along the beam as a result of this stretching. Now what we're going to do is we're going to sum that, so it's the total strain is the axial strain plus the bending strain. And if you remember from the previous lecture, right, here's the bending strain. It's equal to the second derivative of u, so it's the curvature, d squared u dx squared, times y, where y is the distance from the neutral axis. Okay, so y is the distance from the neutral axis here. And so then I evaluated what the bending strain is, and so I just plugged in the trial function here, my displacement shape function, into this second derivative, and so this is what I end up with. And then the strain energy is the integral of the total. So if you remember from before, so we've got basically the total strain now is equal to epsilon A plus epsilon B. Okay? And what I'll do is actually I want to write it, first I'll use a different color. I'm going to write that epsilon T at a point X is equal to epsilon A plus epsilon B of X. Okay, and epsilon A is the constant added strain, axial strain, due to the stretching of the beam. Okay, and I didn't put the dependence on X because it's just a constant. Okay, and so here's the strain energy integral. So we integrate epsilon squared, and we integrate that over the volume. Actually, B is the distance into the page, and the strain is constant over that z direction. So when I integrate over the volume, right, normally I have dx, dx, dy, dz, but I already integrated over z, and that just gave me b because everything's constant, doesn't vary as a function of z. And then the other part of the strain energy integral, it's 1/2 e times the integral of epsilon squared. Right? So if you remember, in general, this is the integral over the volume of 1/2 e times epsilon squared. Whoops, no, sorry. Epsilon squared dx, dy, dz. Right? This is the general form of the strain energy integral. Okay. So in this particular case, I integrate over y, which y varies from minus h over 2 to h over 2, and x varies from minus L over 2 to L over 2. And so I plugged in, here is epsilon b here. Here's epsilon a. So this is bending strain, and this is axial strain. Okay, I plug those in for epsilon. So this is that guy. Okay, and so this term here is the strain due to bending, and this is the strain due to the axial tension. And then I calculated the integral. Oh, aren't you glad that I did this in MathCAD rather than writing it all down? And this is what I end up with. Okay, so this is the total strain energy. And what I want you to notice is that we end up with, so remember that when we do the minimization, we're going to minimize over u naught. Okay, so I have a term that looks like u naught squared, and when I multiply this out, I'll get a u naught to the 4th power. So I'm going to get like w is like some constant. Let's call that like alpha 1 times u naught squared plus alpha 2 times u naught to the 4th power. And so when I evaluate the derivative, I'm just going to use a little bit more space for this. So dw du naught is going to end up being 2 alpha 1 u naught plus 4 alpha 2 u naught cubed. Okay, and this term here, it would be what would give us a linear spring constant, and this term over here is what's going to give us a nonlinear spring constant. And so where did that term come from? It came from this guy, right? Because if you look at the, I'm going to go back to the small size again. If you look at this, this one has a u naught squared, and so when we do the integral, this is what gives us this u naught to the 4th power. Okay, so it's the axial strain is what gives us the nonlinear spring constant. Okay, so let's continue. And so here I define the energy function. U is equal to the strain energy minus the virtual work done by the force. And so then I substituted in my integral here, and this is F times u naught, so that's easy. And now I'm going to find the displacement that minimizes this energy function. And so I evaluate the derivative of big U with respect to u naught, and I get this mess. And so I set that equal to 0. So what I'm doing here is I'm saying du naught is equal to 0, and we're going to, and so we solve this for f. Okay, so this is the setting the derivative of u with respect to u naught equal to 0, and so we get f equals, and it's sort of ugly, I will write it in a slightly cleaner way here. Perhaps not. Let's see. Yes, I'm going to write it in a slightly cleaner way, and so I get pi to the 4th over 8. Sorry. Pi to the 4th over 6 times e b h cubed over L cubed times u naught plus pi to the 4th over 8 times e b h cubed over L cubed times u naught cubed. Okay? So I think I get everything correct in there. Okay, so this is the solution to using this variational method. And just like I promised, right, we got a term. This was in the previous slide, right? I said this would evaluate to. I said that dw du naught would evaluate to some 2 alpha 1, some constant times u naught, and some other constant times u naught cubed. And indeed, this is what we get. So this is the constant multiplied by u naught, and this is the other constant multiplied by u naught cubed. And now the idea is that the spring constant, or the way that we would think about it, this as being a spring constant. So for a spring, we could say that it, like, again, maybe I'll say that the linear spring, we would write that as F is equal to K times u naught. And so in general, we write that F is some function of u naught. And in this particular case, we could see that that's this e b h cubed over L cubed. That's what usually the spring looks like this, right? This is sort of looking like the moment of inertia, and this is the L cubed term. And that's times pi to the 4th over 6 times u naught plus pi to the 4th over 8 times u naught cubed. And so if we want to think about this as, if we want to think about it in terms of it being like a spring constant, we could sort of say that let's write it like this. F is equal to some linear term, I'll call it K1 times U naught plus K sub 3 times U naught cubed. Okay? So I call this K sub 3 because it is the thing that multiplies U naught to the third power. And we could see that K1 is EBH cubed over L cubed times pi to the fourth over 6th. And the K3 is equal to EBH cubed over L cubed times pi to the fourth over 8. Okay? And so we said early on that spring is nonlinear when deflection amplitude U naught is large. And so can we define large? Quantitatively? Okay. So how do we determine what is large amplitude? And so one thing that we could do is we could write the sort of the effective spring constant here. Sorry, I did make one mistake. Now it's propagating throughout this thing. Okay. Yeah, so I cannot factor it quite the way that I did it here. Oh, so I made a mistake here. So if we look at this, the MathCAD solution, the thing that multiplies U naught cubed is, there's only an h here. Okay, so it's not h cubed, it's h. Okay. Otherwise, actually, it turns out the units will be wrong, right? Because h has the units of meters, and also U naught is going to have units of meters too. Okay, so I fixed that one, and I gotta go here, and I gotta fix this too. Okay, so I need to do this. I can do that, and then I have basically end up with an h squared times U naught here, and I end up with pi to the fourth over 8 times U naught cubed. Okay, so that's okay. So I fixed it there, and now I need to fix it here also. So I get this guy is EBH cubed over L cubed. Okay, so I think I fixed it everywhere. So that looks good. Yeah, that looks good. Okay. So let's write, here's like our nonlinear spring terms here. And so how do we determine when this term is important? Okay. Well, the way to do it is to compare the relative sizes of K1 and K3, and we should put them in a way that allows us to equate them. So we could write here's how I want to do it. We can think about this spring force consisting of a linear force term and a nonlinear force term. And so let's figure out when the nonlinear force term and the linear force term are similar. Okay. So we could write that F is equal to the linear force plus, let's call it like F cubic. And so let's figure out what that ratio is. And so that ends up being, I actually have to look on the previous page here. So it's EBH cubed over L cubed, EBH over L cubed times pi to the fourth over 8 times U naught cubed. And the linear term is EBH cubed over L cubed times pi to the fourth over 6 times U naught. Okay. And so a bunch of stuff cancels, fortunately. So that goes away, this goes away, this goes away, this goes away. The pi to the fourth.